Okay, good morning. I think I'll start even though people are not quite all here because it's time. So, sorry, I'd hoped to start Chapter 10 last time, but we'll start it this time. When Ashish comes, we'll have handouts for Chapter 10, the new problem set and the old problem set solutions, as usual. This chapter is about trellis diagrams for block codes, binary linear block codes of the kind that we've seen before. It's actually a much more general notion that applies to, well, linearity is important, although we don't see it very specifically in the trellis diagram, but we'll see that for constructing a unique minimal trellis, linearity is an important aspect, or more generally, it's just the group property of codes that allows us to construct unique minimal trellis diagrams. And I think it's best to motivate this chapter by an example. Here's a nice example of a code that we know very well that has a nice trellis diagram. It's the 844 Reed-Muller code. Just to remind you of how we construct this code, or one of the methods, we had many methods. We take this kind of universal 8 by 8, well, it's a list of eight tuples, and it's a tensor product of this little matrix 3 times. And if we create this, we get a matrix that looks like that, and we just pick the rows that have weight 4 or greater, and they are the generators of the 844 Reed-Muller code. So we'll take those as our set of generators. It's the 16 code words generated by these 4 generators here. This goes back to the first part of the term, but I hope you recall that fairly quickly. Okay, now I'd like to draw a trellis diagram for this code. I don't particularly know why yet. One idea I might have in mind is to do Viterbi algorithm decoding as a maximum likelihood decoding algorithm for this code. So let's see if I can come up with an efficient trellis diagram. That one means one that is, first of all, has relatively few states in it, relatively few branches, would be efficient, has a decoding map for the Viterbi algorithm. And here's a very nice one. This looks sort of like a rate 1/2 4-state trellis diagram. Of course, it's not time invariant. It doesn't go on forever like for convolutional code. For a block code only exists over a finite time. So we're going to get a block trellis that starts at a particular time, that ends at a particular time in a single state. And but we want the basic property that the paths in this trellis are in one-to-one correspondence with the words in the code. So how many words are there in the code? There are 16 in this code. How many paths are there through this trellis? Well, again, it has a very regular structure. There's a 4-way branch here. Wherever you get to, you have a 2-way branch here. You have a 2-way branch here. You have no choice here. So there are 16 possible ways to get through this trellis. 16 trajectories, if you like. And next, let's check if they correspond to all the possible code words. Here's the all 0 code word up here. What's next? Let's check for the generators. Here's one of the generators, 1 1 1 1 0 0 0 0. It's a 1 1 0 0. This is a 1 1 also. 1 1. No, I'm sorry. 1 1 0 0 1 1 0 0. That's right. That's this one going through here. And 1 0 1 0 1 0 1 0. That's here. And what's the last one? All ones. Well, that's up here too. Okay, the all one path. Yeah.
How did you draw the trellis? Like, is there a procedure?
I had side information. Jeannie told me. I know that this is an efficient trellis. Where we'll get to, and I hope today in this lecture, is a turn the crank method of constructing not only a trellis but the minimal possible trellis. All right, so you'll be able to see how starting from a set of 4 generators like this, turn the crank, and I'll produce a trellis for you. Okay? But of course you don't see that yet. I just know that this is a trellis, and it's a nice trellis. It has a nice regular structure. You could decode this with a Viterbi algorithm, and you could see the complexity would be comparable to the complexity of decoding a rate 1/2 4-state convolutional code. And in fact, you remember I compared our example rate 1/2 4-state convolutional code, which had a coding gain of 4 dB, with this code, saying they roughly had the same complexity. And when I said that, this is what I had in mind, that I could decode each of them with a Viterbi algorithm with approximately the same amount of complexity. All right? And unfortunately, this only has a nominal coding gain of 3 dB and an effective coding gain of slightly less than that. So it's not quite as good as the convolutional code. And at the end of the day, we're going to find out that that's kind of typical of comparison between block and convolutional codes of the same trellis complexity. But on the other hand, this is certainly a better way to decode this code, recursive by the Viterbi algorithm, than to do a full maximum likelihood decoding of all 16 code words, which involves just brute force computing the distance to 16 code words. This is, if you like, a more organized way of performing the computation of how far is the received sequence from each of the 16 code words. All right. All right. So the reason we look for trellises of block codes is, first of all, it's better than exhaustive maximum likelihood decoding. It is a maximum likelihood decoding algorithm, since we're going to find that we can construct a trellis for any linear block code, which at worst, it's never going to be more complicated than just enumerating all the code words and doing exhaustive maximum likelihood decoding. And usually, as in this case, it's going to be a more efficient method of doing maximum likelihood decoding. So we will have a general method of maximum likelihood decoding that is more efficient than the exhaustive method. Secondly, there's an interesting link to system theory. I won't make a great deal of this in this course, but what are we really doing here? We're representing a block code as a finite state system. In fact, a linear block code is a finite state linear system, although again the linearity is not terribly transparent from this picture. So we have a linear finite state system, just as we did for the convolutional code. However, it's necessarily time varying. Couldn't possibly be shift invariant because we only have a finite time axis, if you like. The time axis only goes over 4 time units in this particular picture where I've grouped 2 outputs at a time. So that's interesting, and for our purposes, an interesting aspect of this is that we now get a notion of how complex is a block code. All right, so far we've been focused on parameters like NKD, which are all algebraic parameters of the code itself. But we want to know about performance versus complexity. So how complex is the 844 code? Well, now we have a little bit of a handle on it. We can say its complexity is that of a 4-state machine. Okay? So trellis complexity gives us a measure of the complexity of a block code, so that we can, for instance, say that Reed-Muller codes tend to be less complex than BCH codes. I'll try to give some substance to that as we go along. All right, so we get additional parameters that have more to do with what we really care about, which is decoding complexity. And finally, I introduced this subject because it's a stepping stone to where we're really going, is this notion of codes on graphs, which is the underlying concept for the capacity approaching codes that is our goal point. Our whole goal in this course is to get to capacity, specifically on the additive white Gaussian noise channel, and the way that people have found to get to capacity, turbo codes, low density parity check codes. The underlying concept that I'm going to be framing that in is codes on graphs, and this is kind of a code on a very elementary graph. So it's a good way from here to there. All right, so that's why we're taking a little time to look at this subject, even though, as I say, at the end of the day, even though there's a better way of decoding block codes than the ways we've had previously, a better non-algebraic way, it still is not going to turn out to be as good as convolutional codes, which we already know about. All right, any questions on what we're doing, motivation, so forth? Yeah?
One way in which this trellis is different from convolutional codes is that each node doesn't have two things coming out, right?
That's right. It's a little bit more irregular. And this trellis section doesn't look the same. We had a completely mixing trellis section for the convolutional code. This kind of divides it into two halves which don't meet. This basically expresses the code as a certain subcode, and its coset is down here. So it's not quite the same. It looks different. Maybe this will turn out to be interesting. Good observation. Okay, anything else at this point?
This says that this is not a convolutional code. Or maybe we can have more number of states and then it's a convolutional code.
Let's see. It's not a convolutional code. It's not even a terminated convolutional code because it doesn't have the simple shift register type of trellis diagram. At least it's not the kind of convolutional code we know about. But why should it be? Let's open up our minds to more possibilities. All right. We don't really care. The objective that we have in mind here is we're just going to try to come up with the most efficient trellis picture that we can for a block code. And we're going to use the linearity, and we're going to basically try to find as few states as possible at each time. That's going to be our measure of efficiency. That's not the only one you could think of, but it'll turn out that any notion of efficient representation comes down to the same thing. So we'll focus on a minimal state representation of a block code. And you can think of this as an exercise in system theory and minimal realizations of a linear system. This you can view the set of all 16 code words you can view as the set of possible trajectories of a linear system on a time axis of length 8, and we want to find a minimal realization, minimal state realization of that linear system. All right, so that'll make sense to some of you, and it won't make an awful lot of sense to the rest of you. Okay, so we're after a minimal, in the state sense, minimal state complexity, let's say. And let's continue to focus on this example, and let's focus on a particular time. Let's focus on the halfway point here. Where do the state times occur, by the way? They occur between the symbol times. You can think of a state as being associated with a cut between a certain set of symbols, which we call the past, and another set of symbols, which we call the future, again using system theoretic temporal language. All right, so if we make a cut, let's say, and do it over here, states are based on cuts between a past and a future. So the state actually occurs between the fourth and the fifth symbol here, not at either of them. All right, if you want to draw where is the state at time. All right, and let's start with this example, and let's ask if we could find any simpler trellis for this. In other words, let's see if we can have fewer than 4 states at this midpoint. All right. Could we possibly have fewer than 4 states at the midpoint? Well, what's the key property of states? The key property of states is that once you get to a state, that then becomes a summary of all the history that you know about the past. And any past sequence or partial sequence that gets you to this state has to have the same set of possible continuations over here in the future in order for this to be a valid trellis representation. So maybe it will help if I draw this just focusing on the central time. There are two ways to get to this central time. One is to get to what we'll call the 0 state. We can get there by 0, 0, 0, 0 or 1, 1, 1, 1. There's a second state, which we can get to, again, by two paths, which are 0, 0, 1, 1 or 1, 1, 0, 0. There's a third one, which we can get to by 1, 0, 1, 0 or its complement, 0, 1, 0, 1. We'll see that each of these involves a 4 tuple and its complement, and this is 1, 0, 0, 1 or 0, 1, 1, 0. Okay, those are the set of possible past sequences that can get to any of these 4 states. There are 2 of them. Okay, now what this trellis says is that from this state, regardless of how we got here, either of these 2 things, there are 2 possible continuations, which happen to be the same thing. Okay? And the property of state has to be that either of these continuations is a legitimate continuation of either of the paths that it takes to get there. So we now have 4 possible code words that go through this particular state, that pass through this state. All right? And down here, similarly, I think what we have is the same set of code words, right? I think there's complete symmetry, and so forth. So let's ask, could we combine these 2 states? Somehow smush them together into a single state? And the answer is obviously no, because 0, 0, 1, 1 is not a continuation of the all 0 sequence or of the all 1 sequence. And 0, 0, 0, 0 is not a continuation of the 0, 0, 1, 1 sequence or the 1, 1, 0, 0 sequence. All right, so in order, the property of the state is the Markov property. And there are many ways of phrasing this, but this is the defining property of states. Is that if 2 past paths have a future continuation, I hope you understand this language as I introduce it, in common, then all their future continuations are in common. Okay. So if 2 paths, let's say, this is the definition of states. If we can find such a situation, then we can say that these 2 past paths go through the same state at the cut time, because then we can smush them together. You can think of this as our starting from, let's suppose we drew all 16 code words, and we drew here would be a 16-state trellis, and the first 2 elements of it might be 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. And we'd ask, can we smoosh these 2 states together? And the answer is yes, because of this property. Because 0, 0, 0 can also be followed by 1, 1, 1, 1. There are actually 4 states that we're smooshing together here. 1, 1, 1, 1, and 0, 0, 0. These are all legitimate code words, and because they're all legitimate, we can basically break this up into a Cartesian product of 2 paths with 2 futures. All right, and represent all 4 of them by a single state. So that's what states do. All right, if we want a minimal state diagram, we should do this as much as possible. That's not very well defined right now, but we should merge states wherever this property holds. So this implies they go through a common state. And it's if and only if. Okay, so you can see it very concretely from the trellis diagram. This is the property that we need. You can see that for this particular code, we do have the possibility of combining all 16 possible states here into 4, because we can combine them all pairwise in this way. This is going to come from the linear property of the code. That's why everything is so symmetric. But we can't go any further than that. So we can conclude from this is that for the 844 code, the minimal state space at the center has 4 states. As size 4. Okay. And this, for a simple code like this, you can simply see what all the possibilities are, and this is the best we can do. So do you get that? This is fundamental system theory, state realization theory. I don't know where in the curriculum one gets this nowadays. Probably somewhere over towards the control side. Maybe in digital signal processing, but maybe not. All right. But we're doing system theory here. Okay, we all get that? Yeah.
For the Markov property is basically if I have 2 past paths, they have one common feature, then I can say that they have all the common feature.
Yeah, if they go through a common state, that implies this statement. Conversely, if we have a set of past paths and future paths that have this property, then we can define a state. In other words, states are always going to look something like this. We have a set of past paths, we have a set of future paths, and the state is simply a node that they go through such that you can combine any of these paths with any of these futures. It's symmetric. You could say the same thing if 2 futures have a past in common, then they have all their pasts in common. But whenever you have a state representation, let's suppose we have 3 states there, then this is what, just looking at those states and the initial and final states, this is what the code is going to have to look like. Okay, because the property of state is that however you got there, you have to be able to take any of these over here. Otherwise, the trellis is invalid. If not all of these 9 sequences are code words, then it's not a valid trellis representation, or not equivalently, it's not a valid state representation. All right, so if and only if we can draw the thing in this way, we get it. So, for small code, you can just see how much combining you can do. In particular, you can ask, what can the 0, 0 state, 0, 0 pass sequence, what can that be combined with? Well, it can only be combined with sequences that have a 0 first part. So let me introduce now the idea of subcodes. We have a linear code C. Let's define an interval on the time axis, k, k prime, whatever. The subcode C on that interval is the set of all code words elegant way to say it is whose support is in k, k prime. In other words, which are all zero outside, which have all zero symbols outside of this interval that we've identified. All right, so that's just notation. So specifically, let's say the past code with respect to a certain time, like the midpoint there, well, we can define that as the set of all code words that are zero outside the past, the first four symbols, and we can define the future subcode as the set of all code words that are zero outside the future. For this code, what is that? If we list the 16 code words, we make this the past, we make this the future. What are the set of, what is the past subcode here? In this particular case, the past subcode is, of course, the all zero sequence is always in this code, or this sequence, 1110000. It's a linear code of dimension 1, and it consists of these two code words. All right. It is precisely the set of all code words that can be followed by the all zero sequence. All right, so I can read it directly off of this trellis picture here. All right. So everybody with me? The past subcode just consists of those two words. The future subcode consists similarly, looking at the trellis, it's the ones that are all zero outside the future. It can, in other words, can follow a past which is all zero. In other words, it's these two code words. All right, so here are two little subcodes of the code. So by definition, this is a subcode of C. You can, if C is linear, you can quickly convince yourself this is a linear subcode. So it's going to have a certain dimension. It's going to have size equal to a power of 2. It's even going to have a minimum distance that is at least as great as the minimum distance of C because it consists of code words of C, so its minimum non-zero weight is going to be at least as great as that of C. So it has some properties immediately. Okay, these past and future codes seem to have a lot to do with the structure of the trellis up here. In fact, the zero state consists of precisely the sequences that go through the zero state here are not coincidentally the set of all past code words in CP followed by the set of all future code words in CF. Okay. And why is that? That's because the set of all ways of getting to here, getting to this state, have to be the set of all code sequences that can be followed by the all zero sequence. All right. Similarly, the set of all continuations from this state have to be the set of all continuations of the all zero sequence. So the zero state is always going to be a little subtrellis that is going to represent, in effect, you can draw it as a sum or a product of the past and future subcodes. In other words, there's a two-dimensional code that has these two generators, G1, G2, generates a little two-dimensional code. Here's the fourth code word in it, the all one code sequence. And every element in that two-dimensional code goes through the zero state.
What if the all one code word was not a code word? So then
It's whatever it happens to be.
then you would have a separate state just for I mean you could
No,
not combine them into
It doesn't matter. Suppose that CP has dimension 1, CF has dimension 1. That means CP is going to be something like this. Okay? CF is going to be something like this. whatever, y.
This just follows from the linearity.
It
Right?
just follows from linearity, right? And clearly, since C itself was linear, we're allowed to add x, all zeros, to y. That's a code word, because these were both code words in C. All right, so the linearity allows you to fill in this fourth corner of the rectangle, if you like. All right, so CP plus CF is always going to look like this. And we'll always call this the zero state, the state that you get to by the all zero sequence, and that can be followed by the all zero sequence. That's always going to be called the zero state. And it's by linearity, it's always going to look like that. Might not be dimension 1, could have any dimension here. All right. All right. So, we're really beginning to get somewhere now. What do all these other states look like, group theoretically? Cosets. Somebody who said cosets? Good. That's right. So CP plus CF is itself a subcode of C, a two-dimensional subcode. So there are 4 cosets of CP plus CF in C. And we'll see if they correspond to the 4 states. So how do we do this algebraically? Let's draw a generator matrix for C in a certain form. Again, I'll draw the past, the future, and so that's the only division I'm concerned with right now. And let me draw it in general form first. I've defined this past subcode, CP, has certain dimensions, so it has a certain number of generators. So we're going to put up here a set of generators for CP, G of CP. Okay, however many there happen to be. And what's their common characteristic? They all are all 0 in the future. All right, so they're all going to look like that. Okay. Then I'm going to take a set of generators of CF, and similarly I'm going to use them up over there. These are all code words, so and they're clearly linearly independent of those. So I'm on my way to constructing a generator matrix for C. But obviously I'm going to need some more. We can call this number of generators in the past, number of generators in the future. This is the dimension of CP. This is the dimension of CF. And now I need some more generators, which by definition are going to have to span both past and future. Let's see. Since I've already introduced the coset language, let me just mysteriously put that as the generators of a quotient group. C mod CP and CF is what that means. All right, and it's a quotient group if you know or recall what a quotient group is. Anyway, there are K minus KP minus KF of these. And I don't particularly care what I put down in here. Their property is that they have to span both past and future. All right, so for our particular example, here's the generator for the 844 code. What we're talking about is a generator that looks like 1111. That's K past is 1, 0, 0, 0, 1, 1, 1, 1. K future is 1. They're both one-dimensional codes. Then I need 2 other generators which must span past and future. So what'll I take? Let me just take 2 more. 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. That would be one possible choice. And so this is K minus Kp minus Kf, which is 2. Okay. What I'm going to claim is that I'm going to need a state for every possible linear combination of these generators. All right. So claim, well, let me break it down into more logical sequence. Every code word in C can be written as some linear combination of the generators. All right, what does that amount to? It amounts to a certain code word in the past code plus a certain component in the future code, either all 0 or all 1, plus, let me call this the state code, S, as I do in the notes. So in this case, we have a two-dimensional state code. Its elements are 8 tuples. It's just a subcode of the code we started with. So it's not quite clear how it corresponds to states yet. But let me just call that S, a state sequence. All right, and I claim I can break this up because the proof is that for every C in C is equal to a sum of, it's a linear combination of the generators. So I just break that up into the 3 possible parts, and so I get one part that's in the past subcode, one part's in the future subcode, and one that's in this state. So this is the past, this is the future, this is the state. So I just break it up according to this. All right, so the 16 code words can all be written in this way in our particular example. So let's project this code word on the past. What does projection mean? It means you just don't look at the part that's in the future. So we're looking at 4 tuples now. So C projected onto the past, this is the part that lives over here, is equal to, well, if I project the past code word on the past, I basically get the past code word again. I'll maybe write it like that, but it's a little bit redundant. Incidental comment, I can regard this past subcode as either an 8, 1, 4 code, or what is it really? You know, it doesn't live out here. Its support is on these 4. It's really a 4, 1, 4 repetition code that lives on the past. Its support is the past. Similarly, the support here is the future, and it's effectively a 4, 1, 4 repetition code for our example. All right, but formally it's, if we project this on the past, it's a 1-to-1 projection. What happens to the future part? This disappears because the projection of anything in the future code on the past is all 0 by definition. Plus, it's the projection of the state sequence on the past. Could the projection of the state sequence on the past be all 0? This is actually an important point. Could the projection of any linear combination of these generators down here be all 0 in the past? The answer is no by the definition of the future subcode. If I found a linear combination of this that was all 0 in the past, I should add that to the generators of the future subcode. So by defining this in this way, I've forced this to be non-zero, unless, of course, the state sequence itself was 0. The all 0 sequence is in the state code. So for a this is non-zero if S is non-zero. And similarly, if I project a code word on the future, I get this becomes all 0. I get the element of the future code projected on the future plus a state on the future, a state projected on the future. And now I claim further that this means I can draw a trellis as follows. Start from here. For the all 0 sequence, I'll have a bunch of parallel paths going to the 0 state that together add up to the pass subcode. These are precise. One of these is going to be all 0, and these are precisely the ones over here that can be followed by all 0, as I've already claimed. All right, so these are the ones that can be followed by 0, and similarly over here, I'm going to put all the future subcode. These, I will say, these correspond to the state sequence 0. These are the ones where if I put 0 coefficients down here, I just get linear combinations of the past subcode, the future subcode. I'm going to write those as going through all one trellis state. And I believe I've already made the argument that this state, at least, is legitimate. All right? That every combination of something in the past subcode with something in the future subcode is a code word. This is simply the CP plus CF that I wrote before. So I've got one state that represents all of CP plus CF. All right. And now let's take another typical state down here. We'll say this state corresponds to the state sequence S, where S is a general state sequence. Think of it as being non-zero. And what am I going to put on that? I'm going to put CP plus this state sequence projected on the past. And that way I'll get all past projections that are of this form for a specific S projected on the past, allowing this to vary through the past subcode. And similarly over here, I will let the set of all these trellis branches be CF plus the state projected on the future. And so all the things that go through this state here will be CP plus CF plus this particular state sequence. So for each of the state sequences, I claim I can define a state such the set of all past continuations of anything that projects on the past as anything in the past subcode plus a past projection of this state sequence can be combined with anything in the future, CF plus the future continuation of this state sequence. One of these is simply the past projection of the state sequence plus the future projection of the state sequence, and this is S, and by construction, this is a code word in the code. Now, by linearity, I can add any past code word to this past projection, and that's a code word. So any of these elements plus SF, continued by SF, the future projection, is a code word. It's just there we're taking something generated by CP and the state code. And similarly, anything by here comes out here. So, I don't know, I think I've left one or two details undone, but are you convinced that I can define a state in this way such that all of these pasts can be followed by all these futures and they're all code words? In fact, they correspond to this element of this subset of elements of the code. We have examples of it up here. For instance, 0011, or let's see, let's take a past projection 1, 1, 0, 0. Here's a typical state sequence, 1, 1, 0, 0, 1, 1, 0, 0. And I can add to this anything in the past. So I get 0, 0, 1, 1, 1, 1, 0, 0. I can add to it anything, any of these two, anything in the future. So I get 1, 1, 0, 0, 0, 0, 1, 1, and 0, 0, 1, 1, 0, 0, 1, 1. And I claim that all four of these have the state projected on the past equals 1, 1, 0, 0. The state projected on the future is 1, 1, 0, 0. And that any of these pasts can be followed by any of these futures. So this is C past plus C future plus 1, 1, 0, 0, 1, 1, 0, 0. That is the claim. Okay? And furthermore, if I go through this, dot, 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 I'm going to generate everything in C. So this is a partition of C. Into what? S cosets of CP plus CF. Subcode of C. Okay, so algebraically, that's what's going on. But having done this partition, at least with respect to this state space, I can create something which has S states, the size of S, which is, what is this? The dimension of S is the dimension of C minus the dimension of CP minus the dimension of CF. Okay, so I've argued that I can get a state space of this, with this dimension. It's a linear state space, and it has a certain dimension, which is just the dimension of C minus the dimension of the past subcode minus the dimension of the future subcode. It's the number of generators I need for S. All right, so, you know, in the example, I need 2 generators for S, so I get a state space of dimension 2 or size 4. All right, it's just a vector space over F2 in this case. Okay, you all with me? I think you are. I don't see any great puzzles. All right, so I can get at least these few states. Could I get any fewer? Can I possibly merge any 2 of these states? Could I draw a trellis in which, say, I mush the 0 state together with one of these non-zero states? And the answer to that is clearly no, by the definition of the past and the future subcodes. These are all of the future sequences that can follow the all-zero past sequence. There can't be any more down here, so we can't possibly mush them together. And similarly, just by going through this, if you can't take the past part of one state and combine it with the future part of another state sequence, because that clearly is not in the code. And I don't have a slick proof of that in mind at the moment, but there is one in the notes. All right, so this is, we have the conclusion from this is what I call the state space theorem. Given code C, any partition of the time axis, the total index set, into past and future. I can do this not just at the midpoint, I can do this any point along the code that I want to. Any partition into past and future. There the minimal, we get a linear state space in other words, a vector space, S, and the dimension of S is equal to the dimension of C minus the dimension of this past subcode minus the dimension of the future subcode. So we can simply calculate what the minimal dimension of a state space is at any point along here. So for instance, at this point here, what's the minimal size of a state space? What's the past subcode here? What's the set of all code sequences that are all 0 in the future? I'll have all zeros out here. At this point, CP is just 0, 0. Okay, it just has dimension 0. Yeah, 0. What's the future subcode? This is the subcode which has support all out here. This is anything that starts with 0, 0. This is 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1. Let me just write down generators. 1, 1, 1, 1, 0, 0. So this is dimension CP equals 0, dimension CF equals 2. And so the minimum size of the state space is 4 minus 2. It's again 2.
But this needn't be true in general, is it? At each stage, the number of states is the same.
Certainly not true in general. Let me ask about time 3. I can certainly do that. Okay. Time 3, what's the past subcode? This is the code words that have support on the first 3 symbols. Again, that has to have dimension 0 because the minimum weight of this code is 4. So there can't be anything that just looks like 1, 1, 1 and then 5 zeros. What is the future subcode for that? Now the only generator of the future subcode is 0, 1, 1, 1, 1. We have to go this far, and then it's what futures can we get from here? There are only 2 words that are in the future. So in that case, we have dimension past is 0, dimension future is 1. So if we drew a state space here, we would have to have 8 states. In fact, I can do that. If I just draw a little state in the middle of each of these lines, I get now a trellis picture which has an explicit state at this 3rd time here, but it has 8 states. Ooh, ugly. So I've masked that. I've suppressed that by this nice little 4-state trellis. But yeah, if you insisted on drawing a state space at time 3, it would have 8 states in it. All right, we'll get back to that when I get to this turn the crank procedure, if I do, of getting to minimal trellises. All right, so what have we done? We've established that there is a uniquely defined minimal state space size for any partition between past and future. In other words, at any time where you want to make a cut in the time axis between past and future, you can define what the minimal state space size is. And now you might ask the question, can we simultaneously achieve minimal state spaces at all times. In other words, can we draw a single trellis which gets the minimal state space at each time? We haven't proved that there is. It might be that if you push in the state space at one time, it forces the state space to balloon out at another time. And in fact, for nonlinear codes, that is typically what happens. But for linear codes, a minor miracle occurs, and the answer is yes. Okay. So how am I going to prove that? I'm going to prove it via this very handy tool, which is also a construction tool, which is called a trellis-oriented, or a little bit more formally, a minimum span generator matrix. So the idea here is, given a generator matrix, reduce to trellis-oriented form. We're going to prove that this is unique, or effectively unique, and specifies minimal trellis at all times in a certain way. All right, let's start again. So loosely, what is a trellis-oriented generator matrix? Well, if we have a generator, say 0, 0, 1, 1, 1, 1, 0, 0, its span is this interval from its starting time to its ending time. It's this. All right, we say it starts at time 3, it ends at time 6. The span is the interval 3 to 6 in this case. Okay? So we think of this as not being active before time 3. At time 3, we get the first interesting thing happens. A 1 comes up, it then goes through something. These don't have to all be 1s. It could be 1, 1, 0, 1. Then there's a last 1 at some point, and then it quiets down and it's dead again. Yes. Except, I'm not sure. Would you say the support of this was 3, 4, and 6, or would you say it was from 3 to 6, the interval from 3 to 6? I don't know. What's the definition of support?
I don't know.
Okay, I'm not sure I know. It's probably been defined both ways in different literatures. So I'll call it a span, but it's roughly, it's the support of the interesting part. All right, so that's the definition of span. And what a trellis-oriented generator matrix is: a minimal span matrix, meaning all generators have as short a span as possible. Or I'll just say are as short as possible. There's a lecture, I can be loose. Now, it's not even clear that's well defined yet. But let me, again, give you an example and show you how to find a trellis-oriented generating matrix just by example. Let me take our example here, 1100, 1100, 1010, 1010, 111111. So there is a generator matrix that's not in trellis-oriented form. In particular, I can see that by adding this to this, I can make this generator have shorter span. I can replace it by one which is 4 zeros and then 4 ones, which we've already found useful in constructing a trellis. All right? But let me proceed through it more systematically. This generator generates all words in the code. So how can I find a set of linearly independent generators that has shorter span? There's a sort of greedy way of proceeding. Let's take the first two generators. Can I combine these to find anything that has a shorter span that I can replace one of the generators with? Anybody? No, I can't. It's not the answer I expected to hear.
If you add the two, then you get the span of 4 as opposed to 6.
Let's identify what the spans of these are. That has a span of 4. That has a span of 6. That has a span of 7. This has a span of 8. What I'm trying to do is to reduce that.
If you add the first two, you get 4 fours in the middle.
So if I add the first two, that seems like a good thing to do, because then I get 0, 0, 1, 1, and I've reduced the span of that generator. Okay? All right. Any way I can combine these two to reduce the span? Obviously not, because the span of this is completely included in the span of this. If I add these two together, then I'll get something which still starts here and ends here. Why was I able to reduce the span here? Because the spans had the same starting time. So I got a cancellation of the first bit. I got a 0 up here. That's what I wanted. So that's the key to proceeding. If I see any place, any two that have the same starting time, then I can add them together. And the result will be something that has a shorter span than at least one of them. All right, so let me do that. I see two here that have the same starting time. And so I add that to that, and I get 0, 1, 0, 1. So I've got the span down to here. I can do that down here. And I get this, which has a very nice reduction in span. Can I go any further? I could clearly look for the same thing in ending times. If I could find two ending times that were the same, I could do the same trick. Add those two generators together, and the result would be something that was shorter than at least one of the component generators. But here are my starting times, here, 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 and here. They're all different. So I have no possibility for combining two and getting a better starting time. Similarly, the ending times are here, here, and here. They're all different. So I'm done. Okay? So that's how you find a trellis-oriented generator matrix. And there's a closely associated theorem, which is that a generator matrix G is trellis-oriented if and only if all starting times different, all ending times different. Yeah?
What's the definition of all generators are as short as possible?
Oh, I'm now making it. Okay, this is really just motivation. Okay, so this can be my actual definition of a trellis-oriented generator matrix, once I've proved this theorem. It's a matrix in which all the starting times are different and all the ending times are different. And what I've achieved is that all generators are as short as possible. Okay, how would I go about proving this theorem? All right, suppose I have a matrix that's not in this form. Then I've already proved that I can shorten the generators. All right? So if it's not in this form, it's not trellis-oriented. The generators are not as short as possible. All right, so all I need to do is prove the other side. Suppose it is in this form. Then could I possibly find shorter generators? And the proof of that is basically the following lemma, that the subcode C, take any interval kk prime, so given a trellis-oriented generating matrix, namely one that satisfies these conditions, then the subcode consisting of all the code words who have support on this interval is generated by the Gj in G that have support in kk prime. And that's kind of intuitive and obvious. On the one hand, it's clear that any linear combination of these generators is a code word in this subcode. Obviously, if they all have support in this interval, I can't generate anything that has support outside that interval by linear combinations. So the only question is, all right, can I possibly get anything that's in this subcode by having, by combining with a generator that is outside this interval? And again, it's clear that, say, I take kk prime to be here. If I add any if all the starting times are different and all the ending times are different, then I can't, and I start to add generators that are outside here, I can't possibly get cancellation of the starting time, or I can't possibly get cancellation of the ending time. So I'm going to wind up with a code word which has support outside the interval. All right, so it really is a simple lemma.
Anyways, you would have the all zero word, right?
Excuse me?
The all zero word would be part of this subcode. So
This all zero word is always part of the subcode.
Any generator who has something outside this interval, then when you add that with all zero one, you get something that does not belong to this subcode, and therefore that generator could not.
Right, but I have to ask if there's any code word. So I have to consider all the code words, really. But I'm saying if I have a code word C that is some of the generators, and I have a non-zero coefficient here on any generator that has starting time outside this interval or ending time outside this interval, then I can't possibly get cancellation of that non-zero thing. And so if it really requires this to be non-zero, and then I'm going to say then I get a code word that's not in this subcode. Okay, so that's a very quick intuitive sketch of that proof. Again, for writing it out, see the notes. But this lemma then proves this theorem because it now says I can't, if all the starting times are different and all the ending times are different, then I can't possibly get shorter support for any of the generators. And I don't think I said that in a totally convincing way, but that basically is the point here. Yeah?
Does the lemma assume that G is TOGM, or does it assume that the starting times are different in any time?
Well, now I'm defining this, so meaning that all the starting times are different and all the ending times are different. From now on, that's going to be my definition of a trellis-oriented generating matrix. So saying this property implies this property. Okay, but now this lemma has an interesting consequence. This implies for any past and future, CP is the is generated by the generators in a trellis-oriented generating matrix with support in P, and similarly CF is generated by the generators with support in F. So for any P and F, I get a picture that looks like this. All right, I can draw now this boundary anywhere I want, and if the matrix was trellis-oriented, then I'm going to get a certain subset of generators that live in the past, and they'll be the generators, in fact, of CP. They'll be the dimension of them will simply be the number of generators that live in the past for that definition of the past. There'll be some other set that live entirely in the future. Those will be the ones that generate the future. And the ones that are neither wholly in the past nor in the future will generate the state code. So that says I can read off the dimensions of the state spaces just by looking at this single trellis-oriented generator matrix. So now let me very quickly go through the calculation that I went through a little bit laboriously over here. Suppose I make the whole thing the future. In other words, I draw a cut before time 0. Then the state space has dimension 0. All right, all 4 generators live on the future. If I make the cut here, the state space has dimension 1, because 3 of the generators live on the future. 1 is active at time 1. So that means I'm going to get a 2-state trellis at time 1. If I make the cut here between past and future, I see 2 generators live on the future and are inactive, haven't started yet, but 2 of the generators have already started. At this time, we have 3 active generators. Only 1 is still completely on the future. At this time, in the middle, I have 2 generators which past subcode, future subcode, and 2 that aren't. So I get this form that we looked at over there, and I get a state space here generated by these 2 generators of size 2. So just by looking at this, I go right through the picture, and I find the size of the state space at each time. Okay? So there's an algebraic way of finding the minimal state. So now I can draw from this a trellis just by writing down these state spaces. Let me leave these trellises here. Let me draw now a full trellis, or an 8-section trellis. I'm only going to put 1 bit on each trellis. All right, here's the starting state, dimension 0, 1 state. From that I can go out to 0 or 1. label the state spaces. Next time, I'm still just branching. Let's see. Yeah. Actually, to make it look like that, I'm going to want to come down here, 0, 1, 1, 1, 1, 0. Okay. I basically just have 4 states at time 2, corresponding to whatever the first 2 bits are. They all go to different states, because all these have possible future continuations. And I have 8 states at this time, still just branching. Sorry, this is going to take some time to do correctly. And this time, then I come in here, 0, 1. Anyway, and then it's symmetrical on the other side. So that's what a full trellis will look like. And how did I do this trellis? In principle, I wrote down all 16 code words. I wrote down what linear combinations they were up here, and I therefore found what states they went through at each time, and then I just drew the graph that goes through, that describes those trajectories. So I wrote down all the code words, I wrote down all these state codes at all these times. I could have written them down in any order, and then I just connected the dots according to which state, I make this calculation as to which state they go through. Okay. All right, that's a good place to stop. Let me summarize. We now have a method of given a generator matrix for a binary linear block code, of reducing that generator matrix to trellis-oriented form. Just by inspection of the trellis-oriented generator matrix, we can determine what the state space dimensions are at each instant of time, at each possible state cut, and we can then draw a trellis which achieves that minimal state space dimension or minimal state space size for every moment of time simultaneously. And I will assert that this trellis is the minimal trellis in every respect, whether you're trying to minimize state complexity or if you're using the Viterbi algorithm, really what you want to minimize is the number of branches, but there's a calculation about branch spaces in the notes that shows that this also achieves the minimal branch space size at every time, regardless of how you draw the trellis. More elaborate calculations with a more refined notion of Viterbi algorithm complexity still come up with the same result. The result is there is essentially a unique minimal trellis where it's minimal in every way. And this comes from the linear, or more broadly, the group property of the code. So for any linear or group code, there's a well-defined, unique, essentially unique up to relabeling, minimal trellis that achieves the minimum of whatever complexity quantity you want to define. So in this sense, the trellis complexity of a group or linear code is very well defined. It's defined by this minimal trellis or by its parameters, and we can use that as a measure of the complexity of the corresponding group code. And from an engineering point of view, once we've got this minimal trellis, we can use the Viterbi algorithm to do maximum likelihood decoding, just in the same way we did for convolutional codes, sweep from the starting node to the ending node. Okay, digest that, and we'll come back and talk about it again, do a few more details on Monday, but that's the basic idea.